Welcome back, good to have you. So this question's about electric fields. Wow, who would have thought? And to start with, we have an electric field, right? It is a uniform electric field because the field lines are evenly spaced. And question 1A is clearly labeled the positive plate. So these are two charged plates. So charged plates. And to get them charged, a voltage is supplied across them. Right? Because a voltage is a separation of charge. In other words, it gives charges, such as electrons, potential energy. Cool. Now, to draw our field lines, they go from the positive charge to the negative charge. So in this case, our field lines are drawn from top to bottom, which tells me the top plate is positively charged and our bottom plate is negatively charged. Right, and this is just the convention. We draw them from positive to negative. And on the left there, I drew a power supply, and notice that the longer side, the longer line, that corresponds to the positive terminal of the battery, which would be connected to the positive plate of the charged plates. All right, and the small side of the battery is the negative terminal connected to the negative plate. Awesome. Go us, that is an achieved. Very clearly labeled, and we even threw in the words positive and negative. And a battery. Alright, describe the field between the plates and explain how the diagram shows us. Well, we already touched on it being a uniform electric field. So let's jot that down. A uniform electric field. And the question does say, explain how the diagram shows this. So, what of the diagram tells us it is a uniform electric field? Because the field lines are evenly spaced. Cool. And I mean, that is technically enough for the merit. However, let's be a bit more thorough. Another thing we can observe is the closeness of the field lines. If the field lines are very close, it indicates a strong electric field compared to one, let's say, like this, where they are more spread out. So it's hard to tell because we don't have anything to compare it to, but we could also say closeness of field lines indicates electric field strength. All right, and again, since we have nothing to compare it to, it's a bit hard to tell. But what we can tell for certain is that it is a uniform electric field because the field lines are evenly spaced and parallel. Cool. Alright, that would be merit. What's next? Oh, do we have Millikan's experiment? So we have a charged droplet, and it's held stationary between a different set of plates, right? So notice how it's negative on top now and positive on bottom. We're given the voltage across it as 240 volts and the distance between the plates. And part 1, add labeled arrows to show the two forces acting on the stationary droplet. Cool. Alright, so the droplet has a mass and it's carried out on Earth, which tells me there must be a weight force. They don't tell us where Earth is, if Earth is up here or down here, but it's usually safe to assume that Earth is below. So let's just put the Earth in for good measure, and we know that the weight force, weight, is acting down, right, towards the center of mass of Earth. It is not called gravity, it is called weight or gravitational force. Cool, that's one of the forces, but what's keeping it from accelerating down? So it's stationary. In other words, balanced forces, right? To be stationary, it means a constant speed of 0, which means the net force is 0, which means we need an arrow up to counteract weight. That's equal and opposite, indicated by those dashes in case my drawing ability was lackluster there. But what is the force called? So it's a charged droplet inside of an electric field, so it will experience an electrostatic force. So electrostatic force. Right, and in your data booklet, in your formula sheet, you know that that force is equal to the field strength times the charge, right, EQ. Awesome. So, if you got both the labels correct, so electrostatic force or electric or F subscript E, something equivalent, as well as the weight force, and your arrows are the same size and opposite direction vertically, you would get a merit. Alright, and part 2, calculate the number of elementary charges on the stationary droplet. First, start by calculating the weight. Okay, so let's have a think. So, this droplet has a weight force, which is trying to accelerate it down. However, the uniform electric field is pushing it back up with an equal and opposite force as the weight force. Now the droplet, depending on its charge, will experience a different force. Right, so as the number of charge goes up, the force it experiences also goes up. So we need to find exactly how many charges are required to balance against the weight force. So they were very generous and they gave us the formula for the weight force, but you are expected to know that. So the weight force, F subscript W, is the mass of the droplet, which is 5.87 times 10 to the negative 10, already in kgs, so we don't need to convert that. Times g, right, acceleration due to gravity, which we take in NCEA level 2, usually is 9.8. And that gives us 5.75 times 10 to the negative 9, and since it's the weight force, the units are in newtons. Okay, so back to our diagram, we know the weight force, so we know the electrostatic force must have the same magnitude. And recall electrostatic force, Fe, is EQ. And we're looking for Q, right? We're looking for the total charge to then find the number of elementary charges. Do we know E, the electric field strength? Just rereading the question. I don't see it given anywhere. However, we know electric field strength is the voltage across the plates divided by the distance between them. And we are given those two things, 240 volts and 2 centimeters. And of course, 2 centimeters is 2 divided by 100 meters. Right, need to convert our units. So, finding electric field strength first, 240 volts divided by 2 divided by 100, where 2 is in centimeters, so dividing by 100 to convert into meters. And that gives 1.2 times 10 to the 4 volts per meter. Volts per meter. Right? Or equivalently newtons per coulomb. Okay, so let's have a look. We're looking for charge. We have electric field strength, and we know that since the droplet is stationary, the weight force, Fw, must equal the electrostatic force. So let's just write a comment about that. So Fe equals Fw as droplet is stationary. Cool. So now let's solve for Q. So 5.75 times 10 to the negative 9. So that's the weight force, which is equal to the electrostatic force, is equal to E, 1.2 times 10 to the 4, times Q. Right, and so Q, we would divide both sides by 1.2 times 10 to the 4. And that gives 4.79 times 10 to the negative 13. Units for charge is capital C for coulombs. Cool, so have we answered the question? Let's have a look. Calculate the number of elementary charges. Okay, what we've calculated is the total charge. Total charge, which is made up of lots of smaller charges, right? Electrons, or lack of electrons. And so the elementary charge of a proton or an electron is 1.61 times 10 to the negative 19. So to get the number of charges, or excuse me, of elementary charged particles, it is the total charge divided by the elementary charge. Right, so that's the total charge, 4.79 times 10 to the negative 13 coulombs, divided by the elementary charge, 1.61 times 10 to the negative 19, to give us a grand total of 2.98 times 10 to the 6. What are the units? None, because it's just a number, right? A number of elementary charged particles. Phew. Alright, and that would be excellence. So, just recapping this one, because that was a lot. It asked us to calculate the number of elementary charged particles on the droplet. So, we know that to keep it suspended in midair, to keep it stationary, the weight force must have the same magnitude as the electrostatic force. So we found the weight force first, mass times gravity. We then equated it to electrostatic force. However, we needed to find the electric field strength first. So that's what we did, which was the voltage across the plates divided by the distance in meters. So we could then make the statement that those two forces must be equal for it to be stationary. We solved for the total charge on the droplet and divided that by the elementary charge to get the number of elementary charged particles. Alrighty, See ya next time.